Welcome to qnawire.
In this question, by pressing the sides of the book, a frictional force is produced, pointing upwards. We have to discover what is the minimum magnitude of the pressing force that is needed to keep the book in place. In order to answer that question, we have to use Newton's second law. I will choose the following reference frame: a vertical axis pointing upwards and a horizontal axis pointing to the right. Then, applying Newton's second law, the vertical axis results in the following. The net force in the y direction is given by the mass of the book times its acceleration in that direction. It should not be moving, so its acceleration is constrained to be equal to 0. Then the net force is equal to 0. But the net force in the y direction is composed by two forces: the frictional force, which points to the positive y direction, and the weight force, which points to the negative y direction. So the frictional force minus the weight force is equal to 0. Therefore, the frictional force is equal to the weight force. Okay, this is a nice result. Now, let us move to the x direction in order to get something with the force F. So, in the horizontal direction, we have the following. The net force on that direction is equal to the mass of the book times its horizontal acceleration, which is equal to 0 because the book should stay in place. Then, there are two forces acting on the horizontal, and they are equal forces acting on opposite directions. Therefore, we get 0 equals to 0. So, this application of Newton's second law on the horizontal direction have not helped us. Then, what we can do? You can remember that if the force F is the minimum force for the book not to fall, then the frictional force should be the biggest possible frictional force, which, in the case that the book's not moving, is a static frictional force given by the static frictional coefficient times the normal force. But then, what is the normal force that is acting on the book? In this situation, the force F is behaving as the normal force, and there are two forces that are pressing. So we have a normal force that is equal to 2 times F, because the total pressing force is equal to 2 times F. So that's it. Then this gives us the following equation. The static frictional coefficient times F times 2 is equal to the weight force. Then the necessary force is given by the weight force divided by 2 times the static frictional coefficient. Then we have to use the data that the problem gives us, which is that the weight force is 31 newtons and the static frictional coefficient is 0.4. Then the pressing force is given by 31 divided by 2 times 0.4, which is 31 divided by 0.8, and this results in a pressing force of approximately 39 newtons. And this is the answer to this question.